Our first presenter is Dr. Jennifer Miskimins. She introduced herself in part in the beginning, but there's plenty more. As you know, she is a professor and department head of the Petroleum Engineering Department at Mines and holds BS from the Montana College of Mineral Science and Technology, MS and PhD degrees from the Colorado School of Mines, all in petroleum engineering. Jennifer has 30 years of experience in the petroleum industry, starting with Marathon Oil Company as a production and completions engineer and production foreman. She started teaching at Mines in 2002 and has held various appointments since then. From 2013 to 2016, she had a part-time appointment at Mines while working for Beret and Associates, where she specialized in hydraulic fracturing design and post-treatment analysis. In 2016, she returned full-time to the university. Jennifer specializes in well completions, stimulation, hydraulic fracturing, and associated production issues. She is the founder and director of the Fracturing Acidizing Stimulation Technology, FAST, Consortium, and also directs the Center for Earth Materials, Mechanics, and Characterization, CEMMC. Her research interests focus on the optimization of stimulation treatments and the importance of such on associated recovery efficiencies. Jennifer served as the first completions technical director, excuse me, on the SPE International Board of Directors from 2016 to 2018. She was an SPE Distinguished Lecturer in 2010 to 2011 and 2013 to 2014 on hydraulic fracturing in unconventional reservoirs. In 2014, she was awarded the SPE International Completions Optimization and Technology Award, the top technical award in her subdiscipline. Dr. Miskimins serves on a variety of conference organizing committees and as a technical editor for various journals. She is a registered professional engineer in the state of Colorado. And without further ado, Dr. Miskimins.
All right, thanks, Linda. You can hear me okay? I'm gonna voice check with you real quick.
Yeah, I can hear you fine.
Okay. Okay, folks, so I guess I don't mind taking questions during the presentation, but it's probably best if you type them in on chat. I can see those. I've got it pulled up. It might be a little easier than people bouncing in or out audio wise. So, and also we'll have the panel discussion later on that we can come back to any of the topics or questions that you might have. So title, hydraulic fracturing, fact versus fiction. It's really a lot of what this is based on is a lot of the basics that go along with hydraulic fracturing. And I listened to quite a few of your introductions, quite a range of experience and background and everything. So hopefully this presentation is somewhere in the middle of all of your background and knowledge. So we're going to cover real quick just general hydraulic fracturing, why we do it, the importance of conventional versus unconventional reservoirs and why we've seen such an increase in hydraulic fracturing in the North American continent. We'll talk a little bit about the materials that are and how we actually pump these treatments in vertical and horizontal completions. A little bit on some wellbore construction, integrity, and then just a little bit on monitoring of treatments and how some of the techniques that we use to actually see how these things are working. So let's start off with some general hydraulic fracturing. So some terminology for you. What I tell my students and try and remind them quite a bit is that this is a hydraulic fracturing process. So we do other types of fracturing in our industry. This one specifically is hydraulic, which means you have to create a hydraulic pressure and continue to generate that hydraulic pressure as you are pumping the treatment. So we start off with what is known as a pad. A pad is just the name for the initial fluid that we're pumping. At this point in time, we're pumping no solids, i.e. sand or proppant along with it. The intent of the pad is basically to start the rock cracking, start that fracture breaking, and establish some momentum with the rock breaking, and also to create a little bit of width in that fracture to get the sand a place to go. Again, hydraulic pressure, so we're continuing to inject after the pad, and we inject what's known as a slurry. A slurry is just the name, that's the fluid, but now we have the proppant or the actual sand along with the fluid propagating into the fracture and being carried into the fracture itself. Once we generate the crack as far out into the rock and the reservoir as we want, or as we're hoping to design for, we're going to shut down, and we're going to allow the fracture to close. The crack is under quite a bit of earth stress, and the earth wants to close it and get this, this crack in the ground closed back. And what it closes around then is that sand or that proppant that's been pumped out into the crack. Then we start to flow the hydraulic fracturing fluids back to the surface. Ideally, the proppant stays down there, and we're going to start producing the well. So from a side view, this would be a vertical wellbore represented here. The perforations would be shown in the black here, and we're going to create this crack that goes out into the reservoir. Now, by the very nature of Mother Nature, fractures are planar systems, and they will have a directionality to them, meaning that they're going to grow north, south, east, west, depending on the stresses in the ground. So just like when you see a mountain range that's going to break north, south, or east, west, the reason that that mountain range grows the way it does is due to these stresses. Hydraulic fracturing, same thing, it's got a directionality to it. If we were to take, so this is a side view, if we were to take a top-down view of that process that I just described, that's what this picture shows. And so if you think about the wellbore being on the left-hand side of this picture, and the picture, like it says right here, during the time during the fracturing treatment. So at the top of the figure up here, this is the pad being started to be pumped out into the reservoir and to start that crack. So that initial fluid gets pumped, it starts creating this crack. So again, plan view looking down, which means the wellbore's here and the tip of my fracture is out here. So this is the length of my fracture at this point in time. And there's the width of my fracture. Continue to pump the pad. And as I'm pumping the pad, we're generating a little bit more width. Now we start to continue with the slurry. And so we're starting to introduce the sand, or the proppant is the more general name. We continue to pump. This proppant gets distributed out into the fracture. And then what we said, I'm sorry, I was looking at chat. When we stop pumping, the fracture starts to close. And the stresses, I'm going to turn on my video here. Okay. These stresses start to force the crack closed, and the fluid itself then either produces back to the wellbore, or the fluid distributes out here into the reservoir. And that sand now is locked in place and creates this very highly conductive channel that fluids that are out in the reservoir can now flow into that channel and back to the wellbore. So in essence, what the fracture is doing is we're putting kind of an interstate out there that allows the fluid to flow from the reservoir back to the wellbore much easier than it would naturally. So those are kind of cartoons. They show the pictures a little bit of what the process is like. These are actually some pictures of hydraulic fracturing treatments themselves. So what this is from what's known as the Nevada test mine. It's an area that the Los Alamos National Labs They had a vertical wellbore. They hydraulically fractured that vertical wellbore, and then nearby they had some mine drifts, and they dug out those mine drifts back to the fractures. So the fractures, the fluid was actually colored. And so you can see these are just strips of the hydraulic fracturing treatment that showed up when they mined back through it. And on the right-hand side, you can really see the pink. So unlike the pictures back here, we don't just usually have one plane. We usually have several cracks, because it's kind of like taking a sledgehammer to a rock, right? When you take a sledgehammer to a rock, you don't get this nice, good, clean 90-degree angle break. We're going to multiply break some of the rock as we're pumping this fluid. And so you can kind of see how some of these different strands are created down in the wellbore when we're creating those fractures. You also got here's a hand with a rock hammer, kind of give you a scale down there. So we hear a lot about hydraulic fracturing treatments being new. They've actually been around for over 70 years now. This on the left-hand side is a picture of the original fracturing treatment. It was pumped in 1947. It was pumped in Kansas. It was pumped in the Hugoton field, which is still a producing field. Standalone Oil pumped it. It was published in a whopping 8-page paper that kicked off the hydraulic fracturing concept. You will sometimes hear that hydraulic fractures, the first ones were pumped in 1949. Actually, what was pumped in 1949 was the first commercial treatments. So Standalone pumped an experimental treatment. Halliburton, which was a cementing company only at that point in time, pumped 2 commercial treatments in 1949, and they actually held the patent on hydraulic fracturing for quite some time early on. You contrast that with what the basic equipment looks like today, and this is on this is a mid-size treatment. So hydraulic fracturing, from a treatment standpoint and an equipment standpoint, all you need is enough equipment to generate the pressure to break the rock. So in some reservoirs, we can actually pump a hydraulic fracturing treatment with 1 pump truck. In other reservoirs, we're pumping higher rates, we're pumping at higher pressures, so we need more equipment that goes along with it. So think about this picture being, like I said, kind of a mid-size. This is this is a Codell well the picture was taken in the DJ Basin several years ago. So to kind of start off, you have to have some fluid that gives you your hydraulics. So in this case, we've got some water tanks. These water tanks then are holding just a basic water system. On occasion, if we're going to do a lot of treatments or big volume treatments on a location, we might run a pipeline in to this location to minimize the truck traffic associated with it. The tanks themselves then are, the water is, or the hydraulic fluid that we're using then goes into a blender. It's a very creative name because it blends is the purpose. In the blender, you're going to take the water-based fluid. You're going to add in the sand. In this case, this sand right here, this truck has a conveyor belt underneath it that the sand will drop onto that conveyor belt and then dump it into the blender. If we are adding any kind of gel to generate viscosity or any other kind of chemicals to help with the fracturing fluid or the cleanup of the fracturing fluid, this will all be added at this point in time. The blenders are low pressure systems. Most of them are open to atmosphere because we want to be able to go in and take samples off of it to make sure that the chemicals and the blending is all taking place like it should. So think 15 PSI at this point in time. From here then, all of the trucks on the right-hand side and all of the trucks over here on the left-hand side, all these trucks are here for is horsepower. And what we are doing, there's stage system and this manifold right here in the center. A lot of times you'll hear it referred to as a bullet or some kind of pump manifold. All these trucks are here for is to take that low pressure from 15 PSI and generated up to about 6,000, 7,000, 8,000 PSI at the wellhead. These trucks, these particular trucks in this picture are running about 2,200 horsepower each. We have seen a strong increase in efficiency in pump trucks over the last, say, 5 to 7 years. And we do have some trucks out there now that are upwards of 5,000 horsepower. These are probably quads, they're fourplexes. There are some that we have that are quins now. Very efficient, much higher horsepower, so it's nice because it minimizes the amount of equipment you need on location. You kind of got a 2-for-1 truckload from what we had several years ago. So all of these trucks then bring that pressure up, and then the wellhead right here, the BOP is showing in red, and we're just injecting down at the top of the wellhead here at this point. Some of you have probably been on location with some of the shale reservoirs. The shale reservoirs, a lot of times with the horizontal wells themselves, we need to generate more pressure. So we see more trucks on location and more need for volume on location. So generally speaking, we're looking at about, even in 1989, again, this kind of goes back to the fact hydraulic fracturing is really not that new of a technique. 1989, we estimated that, SPE estimated that about 35 to 40% of all wells completed worldwide had been hydraulically fractured. And in the US alone, about 25 to 30% of reserves would not have been producible without hydraulic fracturing. We've used it a lot. We've used it a lot of places around the world. It pretty much can be used in any type of reservoir. It's just it's just about the design and how we actually design for that given reservoir. So why do we do it? Well, a couple of reasons, and again, it's very dependent on the reservoir itself. We will create damage of the permeability or the flow capacity of a reservoir when we drill and when we produce that reservoir. So what hydraulic fracturing does is it can break through what's known as that formation damage from the drilling processes. So we can restore production under those considerations. We also can initiate production. So a lot of our shale reservoirs, the permeability of the reservoir itself is so low that if we didn't hydraulically fracture, we wouldn't be able to flow the oil and gas or the hydrocarbons out of that reservoir. So the hydraulic fracture itself will actually initiate the production and help to, instead of the wellbore going to the reservoir, the fracturing treatment goes from the wellbore to the reservoir and reaches out there into out into the reservoir to allow those molecules a shorter path to get to that point. Overall, what we're really looking at doing is we're looking at increasing the production rate, so how fast the well is producing. But we're also looking at trying to increase reserve recovery. By hydraulically fracturing, we reach further out into the reservoir, which means that well is going to drain more volume, which means we need fewer wells. So hydraulic fracturing actually helps reduce capital needs when we're looking at overall field development. The conventional versus unconventional, so you've heard about that a lot, I'm sure. Really what we're saying is unconventional reservoirs, we've known that they've been here for a while. We drilled through the Barnett for almost 100 years before we figured out how to produce it. And we knew that there was gas there. But what we're looking at with the unconventionals is we get down onto the bottom part of this triangle, which means that there's a big volume there, but the flow capacity is so low. So that's where that hydraulic fracturing comes in to help us generate that flow capacity so that those fluids can flow back to the wellbore as needed. Materials that we use basically boils down to two. You need a fluid and you need a proppant. From a fracturing fluid standpoint, we're not going to go through this entire list. It could take a while, or I can answer questions later. But these are kind of the ideal properties that we're looking for in a fluid. We want it to have the viscosity that we need. We want it to be able to carry that proppant out into the fracture. We're trying to overcome damage, so we're trying to pump a fluid that doesn't create more damage to the permeability of the reservoir. Once we're done pumping the treatment, we want the fracturing fluid to come back out. It just gets in the way of the hydrocarbons themselves flowing into the wellbore. So we want the frac fluid back out of the way. And we want something to be cost effective, of course. Water tends to fit a good majority of those. It's also obviously very safe compared to some of the other options. But anything that can be a fluid and that can generate that hydraulic pressure is going to help us create the hydraulic fracture and can be used for fracturing purposes. The proppant, we traditionally have what's called white sand and brown sand. White sand is just one crystal. Brown sand has multiple crystals, and that's why it gives it the brown color. White sand tends to come from the Ottawa Formation around the Great Lakes area. Brown sand has historically come from Brady, Texas in the Hickory Formation. Now we're using a lot of regional sands because they're not as high a quality of sand, but the cost-benefit ratio is there because there's less transportation associated with it. We can also use ceramics as a proppant. These are manufactured, but they're manufactured from clay. So they're a natural material, but it's just like making a clay pot. We form them into a particle, and then we run them through a kiln and fire them just like you do a clay pot. Makes them really, really hard and really, really strong. So from a completion standpoint, I've got this exact same picture on my background right now. This is the Piceance Basin vertical well pad system. And so the vertical wells, directionally, they go kind of straight down and then they S-curve off. And these vertical wells are intended to enter the reservoir in a vertical orientation. From a horizontal standpoint, again, we've got a pad, we drill down, we kick off, and then we create a horizontal. And in this picture, all these little tick marks down here represent hydraulic fractures. Well, in a vertical orientation, we'll also pump multiple fracturing treatments. Like these vertical wells in the Piceance Basin were probably had about 20 fracturing treatments because fracs don't like to grow in height. They like to grow out. It's path of least resistance. They're lazy, and rocks are very layered. So they don't allow the fractures to grow up through the rock as easy as they grow out. So in vertical wells, if we have a vertical orientation, it usually means that we have a very, very thick reservoir that we are pumping multiple frac treatments up through that reservoir. In this case, this is kind of representing a shale play that has, relatively speaking, a fairly thin reservoir system. And so we're entering that reservoir with these horizontal wells. And then again, the molecules of gas or hydrocarbons don't like to go very far. So we put multiple fracs out there to actually reach out to different areas of the reservoir and drain those particular areas of the reservoir. We always want to have good well integrity. And I know as regulation folks, this is something that you focus a lot on. I think it's something that the industry has definitely focused a lot on. The fractures are not going to grow to the surface. Again, the rocks are such and the stresses are such that fracs are lazy. They're not going to grow that direction. But we obviously want to make sure that we have very good wellbore integrity because we are generating such high pressures that the potential is, the weakness potential is usually in the reservoir, the wellbore itself. And getting that fracture to be isolated and to go where we want it to in the reservoir system. From a monitoring standpoint, we have a lot of different tools that monitor fracturing treatments. Some are pressure-based. Some are actually physically measuring a characteristic of the rock. I'm only mentioning a couple today. This could be something we could spend hours on with diagnostics. But some of you might have heard of companies doing microseismic. What microseismic is in essence, here's the well in the center. We are fracturing this well. Well, when you fracture a well, you break it, you're breaking the rock. When you break rock, it makes noise. So what microseismic is we have geophones or listening devices either in an offset well or possibly on the surface that we triangulate back to where those breaks are occurring. Now it's not an exact science. We can't say within inches that this is where the break occurred, but we can usually say within several tens of feet that we're somewhere in this vicinity that the rock broke. In essence, what it is it's earthquake science. Just like when you hear the epicenter of the earthquake was in Mexico City, we know how fast sound waves travel through the earth, and we can triangulate back when the earthquake happened and how fast those waves moved to locate them. It's a velocity, time, distance relationship. Well, we're doing the same with microseismic, just on a little bit smaller scale. So when we do break the rock, this is a vertical well here. This vertical well, we've got some microseisms that have occurred right here. Each one of these little diamonds is where we have triangulated back that we heard some of the rock breaking. How big are those breaks, or how big are those magnitudes? This is a moment scale on the left-hand side. So you think about, well, we had an earthquake that was a 4.0 or an earthquake that was a 5.0. Microseismic by its very name is sub-zero. And so what we usually see is we usually see microseismic events that are in the -2 or -3 range. It's very equivalent to like a firework going off. So when we see one of these breaks back here, that's the location that we heard kind of a snap that was similar to about an explosive value of a firecracker. So this is a picture from Jonah Field. It's out of Wyoming. This is the Wellbore depth. And what I want to show here is this is those multiple fracturing treatments that I mentioned. At each one of these depths, a different frac treatment was pumped. The little dots that you can see are the microseisms that occurred, and then we've kind of drawn ellipses on top of the microseisms that were associated with each of those fracturing treatments. And so this kind of gives a two-scale visualization of these multiple stacked fracturing treatments in a reservoir system. The last thing I'm just going to mention, we've started to see fiber optics used in hydraulic fracturing. So we literally run fiber, just like the fiber that comes to your house for an internet connection. We run these down in a well, and this can be strapped to the casing. It can be cemented in place. It's not a cheap endeavor by any means, and it takes a lot of care to do it. But what we get, and try and explain this to you, excuse me, excuse me, this is a horizontal well. So this down here is the toe of the horizontal well. This is where the first fracturing treatment was pumped. The blue is where the next fracturing treatment, this pink is where the next fracturing, and each one of these green triangles shows a perforation system. Well, what we're looking at here is temperature that the fiber has picked up. And so the red is the hot part of the Eagleford. When we pump fracturing fluids down the wellbore to hydraulically fracture this first stage, we cool the wellbore down, and the fiber picks that up. And what that means is we can determine how much fluid is actually exiting each one of those perforation clusters. This is the first stage, then we set our bridge plug. This is our second stage, fracturing this stage, and so the x-axis down here is actually time. And so fiber allows us to see where the temperature of the fluids is changing. We can actually also hear fluids, and we can hear proppant exiting out some of the perforations. So that's the quick and dirty. I will leave it at that. And sorry, Linda, I ran a couple minutes over time. I could take a question or two, or we can wait for the panel, Linda, whatever you want to do.
So we have at least we have about 5 minutes. So
Okay.
if we want to take some questions, or we can transition.
Sure.
So if you would like to unmute yourself and ask a question, or put it into the chat, we will manage it from there. Okay, I'm not seeing anything come up from chat. If you would like to ask a question verbally, I know some of you are on mute, so.
Not used to talking about this subject and not having any questions. You usually get hammered with them.
This is David Ring. Where's the propant made, the non-sand propant? Where are they
The
manufactured?
ceramic stuff? Yeah.
Yeah.
So in the US, most of it is actually made in Alabama and Mississippi. The clay systems that we make them from it's a kaolinite clay, and that's actually the location of where a good source of mining for that clay is located in the US. So in the US, quite a few of them are made, I mean, quite a bit of that's made in that particular area. There are international companies that also make it. There's some that's made out of China, some's made in Australia, but for the US and Canada, because we just ship it across the border from those two states.
Is it a lot more expensive?
Oh yeah, yeah. It is, prices are really hard to keep up with, but you can safely say that some of that stuff is around 6 to 10 times per pound what sand is. From a market standpoint, 99% of what we're pumping worldwide right now is sand. So it's a very niche market. So why would you use it? It's really, really, really strong. Yeah. So if we are in deep, hot wells that have really high pressures, that tends to be the only thing that doesn't get crushed. And so we'll use it in those areas. But in all honesty, right now, ceramic manufacturers are suffering significantly. There's quite a few of them that have started to go bankrupt because of the current economic situation.
Thank you.
Craig Hagee, Virginia. I was wondering about the sintered bauxite. Do they still use it as a proppant?
Yeah. In fact, that's that kind of falls into that artificial category. With the ceramics, we have some that are kaolinite. The highest end that we have is actually made from bauxite. Yeah, bauxite, to give you an idea, sand will crush at about 6,000 PSI. Ceramics, the kaolinite stuff will crush at about 10,000 PSI. Bauxite will actually go up to 18,000 PSI. And so, and it's a little bit better in temperature. I'm working on a geothermal project right now, and we're actually looking at using bauxite because that's the only thing that can withstand the pressures. So.
Do they have a distinct azimuth that the fractures run on out that way?
It depends on what basin you're in. Yeah, so really, generally speaking, well, okay, so like in the DJ Basin out here, they tend to want to run east-west because of the Rocky Mountains. Mm-hmm. You go up into the Green River Basin up in Wyoming, we tend to have a little bit more northwest. I'm sorry, north-south. Out where you are, it's a little bit of a, more of a mixed bag.
Like northwest, east,
a bit more tectonics going on, yeah.
Northeast, southwest.
Yeah.
Thank you.
Yeah, of course.
We have about another minute and a half for any other follow-up questions.
Jennifer, this is Larry Harlan. So kind of under the category of fact versus fiction, how do you, as from an academic standpoint, how do you respond to those that are, of the mindset that hydraulic fracturing is in fact harming water aquifers and harmful to the environment from the operation standpoint?
Well, that's not a loaded question at all, Larry.
Yes, it is.
Okay, so I've done a lot with public relations in this area. What I find is there is a group, let's say 10%, that no matter what you say, you will never change their mind. So I've kind of in my world just kind of said, okay, I can't, if they're not willing to listen, if they're not willing to change their mind, then I can't win that battle. So what then I do is I tend to focus on the other 90%, which means that a lot of times what I try and get people to understand is this is not a technique that you can understand in a 30-second news soundbite. Give me 30 minutes and we can talk about the science behind it. Because there's been a lot of, I usually start off with the fact that this is not something new. This is something that's been done for a very long time. It didn't just all of a sudden miraculously appear in the 2000s with shale reservoirs. So I try and walk people a little bit through the fact that there is quite a bit of science behind it. And it's science that has been contributed to from a lot of different areas. And start with that and start to then kind of walk through some of the concerns like, okay, the fracturing fluid concerns, the causing of earthquakes concerns, and just try and put a little bit more of a comfort feel on that there really is quite a bit of science behind it. So I don't know if that helps at all, but like I said, some people you're just not going to win the battle with, but if you have some folks that are willing to listen, I've had a lot of even landowners or royalty owners attend presentations that have come up to me afterwards and said, thanks, because for the first time in 10 years, we understand a little bit more about what they're doing out there. So I think it's just education.
Okay. All right, Jennifer, there is a question in the chat, but maybe you can hang on to that one and we'll take it up during the panel session.
Oh,
We'll move. Unless
can I answer this one real quick?
Sure, of course.
I don't want to throw you too far off. Yes, there will be an appetite for refracturing in horizontal wells. Generally speaking, there's going to be a different reason for doing it. In vertical wells, the fractures over time, because of the depletion, the pressure changes and they'll grow in a different direction. With horizontal wells, we don't always do a good job initially treating the wells, which is something that the fiber optics has started to show us. So yeah, I think you will start to, and we have started to see hydraulic refracturing happen in horizontal wells, especially in economic conditions like right now, because it's cheaper than drilling new wells. So for different reasons, but yeah, we'll start to see it. I think we already have. So, okay, Linda, I'll hand it back to you.